All right, today we are starting chapter 7, where we're going to learn about something called a normal probability distribution. This is probably the biggest idea in all of calculus, or sorry, statistics, because everything from this point is going to build on the idea of a normal distribution. Every chapter that we have from here on out is going to refer back to what it means for something to be normal. But before we jump into normality, we're actually going to talk about a uniform distribution first, and then we'll talk about what it means to be a normal curve. What are those properties, and how can we calculate area from within that? So, in the idea of a uniform distribution, suppose that UPS is going to deliver a package to your front door, and you know that it's going to be sometime between 10 and 11, but you don't know when in there. We're going to let our random variable, which we learned about in our last chapters, x, represent the time from 10 a.m. when the delivery will take place. So it could happen right at 10 o'clock, and that would be x is 0, or it could happen at 11 o'clock, and that would be x is 60. And so we could count from 0 to 60, and it's equally likely to happen at any point within there. So it could happen just as likely between 10:15 and 10:16 as 10:40 to 10:41. So this is called a uniform distribution because any two intervals within that 0 to 60 are going to have the equal probability. So a probability density function, when we think of function, you learn that word back in algebra, we think of equations. So a density function is an equation that's used to compute probabilities of of continuous random variables. It has to satisfy the following two properties. The area under the curve needs to be equal to 1 because one of our conditions of probability that we've learned about so far is that total probability options have to add up to 1. And the height of the graph is going to represent those probabilities, so that always needs to be greater than or equal to 0. So this graph would represent that uniform distribution of when is our package going to arrive. Since we need the length of the rectangle to be from 0 to 60 along that x-axis, if we need the area under this curve to be equal to 1, we can think back to what we learned in geometry about area of a rectangle being equal to length times width. So the height of this rectangle would have to be 1/60th. 1/60th times 60, our total area then is 1. All the values are bigger than 0, so it meets that criteria as well. So then we could find the probability for any interval by looking for the area of that interval. So if I wanted to know what's the probability that the package is going to arrive between 10:15 and 10:30 because maybe I have a quick errand to run and I want to know, what are the chances that I'm going to end up missing the delivery and maybe I have to sign for it. So I can find what is the probability between 15 and 30. And so the length from 15 to 30 along our x-axis would be 15 times the 1/60th if we do again, area of a rectangle, length times width, and so we get 25%, or 0.25 is our probability that that package would arrive within those 15 minutes, and we could end up missing delivery if we choose to run that errand. Now, uniform distributions, nice flat distribution, and we can think about length times width, but more often what we're going to be concerned with is called a normal distribution. So this is a graph of a normal distribution curve. Two main characteristics are that it is symmetric and it is bell-shaped. A continuous random variable is normally distributed or has a normal probability distribution if its relative frequency histogram, so relative frequency, we're talking about the percent of that happening as its decimal form, the relative frequency histogram of the random variable has the shape of a normal curve. So back in that last slide, we saw the histogram there, and then that red curve is drawn onto it to show that normal shape. So if our histogram is symmetrical and bell curved, then we can say that it follows this normal distribution. Now, for those of you who are in calculus or have taken calculus, you will know what those inflection points are. Inflection points are the points on a curve where over on that left-hand side, it keeps increasing in steepness until it gets to the inflection point, and then the curve is still increasing, but the steepness is decreasing. Or we're thinking about the slope is becoming less steep after that point. Those happen, as it shows on the bottom, a standard deviation away from the mean. So in a normal distribution, our mean should be exactly in the middle of the curve at the peak, and then we can add and subtract a standard deviation out to each side, and we will find those inflection points. So these are some different normal distribution curves. So we have the top one in red there has a mean of 0. The mean should be exactly in the middle, and then a standard deviation of 1, taking a step of 1 out to each side. The blue one has a mean of 3. Again, right at the peak, we find the mean. Take a step out to each side of length 1, so our standard deviation is 1. Now down at the bottom, you've probably seen graphs that look like this a lot lately with the hashtag flatten the curve, right? So we see the red one there has the mean of 0 and a standard deviation of 1, and it's a very tall graph because it has to fit all the area underneath it. But in that blue one, as we increase the standard deviation to 2, the curve becomes a shorter graph. So you, I'm sure, have been seeing a lot of pictures like that lately in the news or on social media. So here's some properties of that normal density curve. It is symmetric about its mean. The mean, median, and mode should all be the same, and so it's going to have that one single peak, and that's going to happen at the mean. It has inflection points, one standard deviation away on each side. The total area underneath the curve is 1. And because it's completely symmetrical, the area to each side of the mean equals 1/2. As x gets bigger and bigger and bigger and bigger forever, we're going to approach in algebra what we called an asymptote. The graph will get closer and closer to that horizontal axis, but we'll never actually reach it because one of our characteristics of a probability curve is that it always needs to be greater than or equal to 0. So it'll get closer and closer to that 0 line. And then earlier this year, we learned the 68, 95, 99.7 rule. That applies to our normal distribution curves. So as we take one step out to each side, we find those inflection points, and we also find 68% of the data as we take one step out to each side in both directions. We find 95% within 2 steps out and 99.7 within 3 steps out. And this again is familiar. We have done this earlier this year. So on our next slide, we have some data that represent the heights of a random sample of 50 2-year-old males, so toddlers, 50 toddlers. We're going to draw a histogram, and it says what our class sizes are going to be there, that we're going to start at 31.5 and have a class width of 1. Now remember, when we choose to create class widths of different size, it can change the way the histogram looks. So they're giving us some direction here in how to create that histogram. And then we want to look at that and decide, does that look normally distributed to us? So here's all of our data, and on a homework problem, we could toss that all into StatCrunch and create our histogram there in StatCrunch. So this is what our output histogram would look like. So again, on our x-axis, we can see it begins at 31.5 like they specified, and each class width is 1. And as we look at that, we want to say, does that look like a normal distribution curve? And the main things we want to think about, does it have one peak? Is it symmetrical? And is it bell-shaped? And yes, that pretty much fits all of those characteristics. We only have one peak there at about 36, we would say. So that would be our mean, median, and mode for this data. And then the bars are almost perfectly symmetrical. We see a little bit of a difference in that second bar out, but nothing enough to cause any concern. So on the next slide, we put the density curve on top of that histogram, and we want to know, how does the area of the rectangle correspond to the height of between 34.5 and 35.5. How does that relate? So here is that same histogram with the density curve drawn onto the top. And then if we want to know what's happening between 34.5 and 35.5, we know which rectangle we're looking at. And that looks like it might be still less than one standard deviation away as we think about where those inflection points on that curve would be. So as we think about the area underneath the normal curve, suppose that a random variable x is normally distributed with a mean of our mu and a standard deviation of sigma. The area under the normal curve for any interval of values represents either. Now really it represents both. It's just different ways of wording the same thing. It's not an either or, it's a both. We could just word it either way. It represents the proportion of the population with that characteristic, and it also represents the probability that a randomly selected individual from the population will have that characteristic. So for example, if we know that the weights of giraffes are approximately normally distributed, they have a mean of 2,200 pounds and a standard deviation of 200 pounds. We're going to draw a curve and label in those parameters. We're going to shade the area under the curve to the left of 2,100 pounds. And then we want to suppose that our area under the normal curve to the left of 2,100 is 0.3085. And we want to say, what does that mean about this? So drawing in our normal distribution curve, we're going to put our mean right there in the center, so 2,200 pounds right in the center. And if our standard deviation is 200, we'd want to count by 200s out to each side. Now, it looks like they only counted by the 100 because the next question then has 2,100 as the key value they were talking about. But we'd want to make sure that we're paying attention to where those sigma markers would be. So our first sigma marker would be at 2,000 and 2,400. So in your homework assignments, those will be the markings that you will see. Then in part B, we wanted to shade in the area to the left of 2,100. And then it says if that area is 0.3085, what does that mean about this? Well, that means that the proportion of giraffes whose weight is less than 2,100 pounds is 0.3085. And the probability that a randomly selected giraffe would weigh less than 2,100 pounds is 0.3085. So in other words, if a zoo had 100 giraffes, which would be kind of insane, but if they did have 100 giraffes, we would expect about 31 of those giraffes to have a weight less than 2,100 pounds, thinking about it as the probability. So about 31% of them are going to have that weight. Or if I just went to a zoo and I randomly selected one giraffe, I'd have about a 31% chance of selecting a giraffe whose weight is less than 2,100 pounds. That's the end of 7.1. We'll pick up with 7.2 another day.